Have you ever actually stopped to wonder how a computer makes sense of a photograph? I mean, to us, a picture is instantly recognizable, right? It's a landscape, a face, maybe a car. But to a machine, it's literally just a massive, overwhelming grid of numbers representing pixel intensities. So how does an algorithm actually translate that sea of raw data into real-world objects? Well, welcome to this explainer. Today we're going to demystify this whole process by exploring local and regional processing, and we'll uncover exactly how computers learn to see shapes.
Okay, here is our roadmap for today. First, making sense of pixels, then local processing, microview, followed by the steps of local processing. After that, we'll hit regional processing, macroview, the steps of regional processing, and finally, we'll do a head-to-head with local versus regional processing. Let's get into it.
Section 1. Making sense of pixels, building the foundation.
To get us started, I really want you to think about this core conceptual question. How do computers see objects? When you or I look at a picture of a forest, we immediately distinguish the individual trees from the sky in the background. It's effortless, but a computer, it just sees a matrix of light and dark values. The immense, and I mean literally immense, challenge in computer vision is finding a reliable way to group those values together to find meaningful, continuous boundaries.
And that brings us to the ultimate goal of all these techniques we'll be talking about: image segmentation. Basically, this is the process of partitioning an image by assigning a class label to every single pixel based on shared characteristics. That could be its color, its texture, or its shape. Think of it kind of like taking that picture of a forest and literally tagging every single pixel that belongs to a tree with the label tree, completely isolating the objects from the background. Local and regional processing are essentially just two completely different algorithmic strategies to achieve this exact goal.
Moving on to Section 2. Local processing, microview.
First up is the micro approach. Local processing works by transforming an input pixel's value based on a very small neighborhood of surrounding pixels, rather than trying to look at the entire image all at once. Imagine you're standing right up close to a giant mosaic artwork. Local processing is like ignoring the whole picture entirely and focusing solely on how one single individual tile relates to the 8 immediate tiles touching it in a tiny 3x3 grid.
So let's look at what makes this method tick. By calculating a new output image based on subsets of pixels, usually like a 3x3 or maybe a 7x7 grid, local processing becomes incredibly powerful for feature extraction. It absolutely excels at finding sharp, rapid changes in image intensity. We know those as edges or corners. To actually do this, it utilizes operators like linear filters and nonlinear morphological filters. You can think of linear filters almost like a blur tool used to smooth out background noise, while median filters act more like a highly specialized vacuum, just sucking up stray pixels while keeping those important edges incredibly sharp.
These core techniques are absolutely fundamental for image enhancement and edge detection using what are called convolution masks. It allows for localized contrast improvements. So, for example, if one part of an image is just poorly lit, local histogram processing can go in and adjust just that specific region without blowing out the lighting in the rest of the image. It is super precise.
All right, Section 3. Steps of local processing.
In the world of image processing, simply detecting an edge isn't really enough, because you often end up with broken, fragmented lines. You actually need to link them together. So first, the algorithm computes gradient arrays, which is really just a fancy way of the computer asking, hey, where's the color changing the fastest and in what direction? Next, it creates a binary image using a threshold. Really strong changes become a 1, which creates an edge, while everything else just drops to a 0. Now, to fix any broken lines, it basically scans the rows of the image and fills in tiny gaps of zeros, turning them into 1s to connect the line. Finally, it rotates the image to catch any vertical or diagonal gaps it might have missed. The mathematical logic running under the hood here acts like a highly precise, pixel-by-pixel sieve. If you dive into the equation for creating that binary image, a pixel only becomes a 1 if its gradient magnitude is greater than a very specific threshold, and its angle falls within an acceptable band. And boom, it leaves us with continuous, perfectly connected edge lines. Stepping back, let's hit Section 4. Regional processing, macroview. If local processing is like looking at a single mosaic tile with a magnifying glass to find sharp edges, regional processing is taking several giant steps back to look at the whole wall. This refers to techniques that partition an image into homogeneous, connected regions based on shared properties. Think broad areas of similar intensity, texture, or color. Instead of trying to find the sharp boundary of a cloud,
It tries to find all the connected blue pixels that make up the sky behind it.
The crucial takeaway here is that these techniques operate on an entirely different philosophy than edge detection. The core techniques include region growing, where the algorithm starts at a tiny seed and just grows outward. Then there's region splitting and merging, where it takes the whole image and recursively chops it into quadrants until the regions are uniform. And finally, watershed segmentation, which is a really fascinating method that treats pixel brightness like a literal 3D landscape.
Because regional processing relies on pixel similarity rather than looking for abrupt changes in boundaries. It is a fantastic approach when you're dealing with images where the edges are just blurry or really unclear. It fundamentally focuses on pixel homogeneity above all else.
Section 5. Steps of regional processing. Let's visualize this. Imagine spilling a single drop of water on a paper towel. That drop is our seed point. The algorithm evaluates the surrounding pixels, and if they share a specific color or intensity, it absorbs them. It recursively appends matching pixels that touch it horizontally, vertically, or diagonally, just blooming outward until it finally hits a boundary. Once it can't grow anymore, that entire connected component is locked in and labeled with a unique region label. And just like that, you've segmented an entire object right from the inside out.
Now, the watershed algorithm takes a wildly creative approach to this. It views the image as a 3D topographic map. The dark valleys represent regional minima, and the bright edges represent high ridges. Imagine punching a hole in the bottom of those valleys and flooding them with virtual water from below. As the water rises, distinct catchment basins start to fill up. When the water from two different basins is about to merge, the algorithm essentially builds a dam to keep them separate. Those dams become your continuous, perfectly closed segmentation boundaries. Honestly, it is a highly effective way to separate touching or overlapping objects.
Bringing it all together in Section 6, Local versus Regional Processing.
So how do they actually compare? Well, a computer's choice between these two foundational approaches depends entirely on its end goal. Local processing is your go-to for incredibly detailed feature extraction. If you absolutely need to find sharp edges, fine lines, and tiny corners, local processing is super fast and effective. But it is highly sensitive to stray noise. On the flip side, regional processing is an absolute powerhouse for handling noisy images because it looks at broader uniformity. It practically guarantees closed, continuous regions, which makes it amazing for things like analyzing medical tissue imaging. However, this macro-level grouping and recursive growing is computationally expensive, and it can be prone to over-segmentation if it's not tuned perfectly.
Ultimately, whether an algorithm is looking through a microscopic lens to find a sharp edge, or it's flooding a virtual topographic map to separate out shapes, these foundational rules of pixel grouping are exactly what allow machines to understand our world today. So, the next time you see a self-driving car perfectly outline a pedestrian in the pouring rain, ask yourself, is it looking at the individual tiles, or is it seeing the whole mosaic? Keep exploring, keep learning, and I'll catch you in the next explainer.